So going back to a couple of ideas that we talked about in previous chapters, recall that there are two different types or major types of compounds. There's ionic compounds and covalent compounds, ionically bonded substances and covalently bonded substances. And a couple of things about aqueous solutions. So these substances, when they're thrown into solution, they do two very, very different things. Generally speaking, when you throw an ionic compound into water, it dissolves, it breaks apart. Breaks apart in particular into its component ions. And so what's happening on a very, very small scale is that, say you have, for instance, sodium chloride. You throw that into water. It's got this crystal structure. It looks like this, where you got the little chlorine anions and the sodium cations. Actually, it's probably backwards. These are probably the cations and these are the anions. But anyway, remember that water is very polar. It's a polar molecule. It's got a partial positive charge and partial negative charge. And so what's going on with water is that it'll come in and essentially surround each of these ions. So this is the chlorine anion. It'll associate itself so that those partial positive charges on the hydrogen will balance out the negative charge on the chlorine and just take away that particular ion. And then a different set of water molecules will come in and take away one of the cations, one of the sodiums, and so on and so forth. And so what happens is that these ions, they separate or dissociate from each other in solution, and they go apart and they break apart. So when you take sodium chloride and put it into water, you end up getting sodium ions, and what we do is say they're aqueous, that is, they're dissolved, and chlorine ions that are aqueous and dissolved. And so they're completely dissociated. Now, the reason why this happens, again, is because those waters are solvating or surrounding them and balancing out those particular charges. Now, contrast that with what happens when we throw a molecular compound in there. Say we throw some methanol into an aqueous solution. These are not ionic. They aren't ions. The particular atoms in there are covalently bonded. And so it does not dissociate, methanol does not dissociate into ions when put into solution. It may dissolve in water, it may actually go into water and you won't see it as separate from the rest of the water, but it doesn't dissociate. And so we also call this aqueous, but in the case of a covalently bonded compound, we show it like this, where that whole molecule stays as a molecule and doesn't break apart into its associated ions. So these ions in solution are really, really important, and that is because they can conduct, for one reason, they can conduct electricity. So if you were to take water and hook it up to a battery, okay, so put an electrode hooked up to a battery into water and put the other electrode to a light bulb, you couldn't actually conduct electricity through pure water. There's no ions in solution to conduct electricity. However, if you take a sample of water that's pure water and dump some sodium chloride into them, now all of a sudden you have ions. You have these positively charged species and negatively charged species. And electricity is just the movement of charged species. And so an ionic solution can actually conduct electricity. So aqueous solutions that contain ions can conduct electricity, and so they're called electrolytes or electrolytic solutions. Something like sugar. Sugar is so sucrose is a molecularly bonded molecule. It's a molecule. It's not an ionic compound. And so if you took sugar, so table sugar, regular sugar, you threw it into water, what you would find is that even though it's an aqueous solution, it doesn't actually contain ions, and so you would not be able to conduct electricity through this solution because there's no ions to conduct that electric current. And so this concept of electrolytes important for this reason. It allows us to see what actually ionizes and what does not ionize when we put into solution. So when an ionic compound dissolves, the relative concentration of those ions in solution depend on the chemical formula of the compound. So if you were to dissolve 1 molar, so a 1 molar solution, or if you had a 1 molar solution of sodium chloride, the solution would have would be 1 molar in sodium ions and 1 molar in chlorine ions. Well, if it's 1 molar in sodium ions and 1 molar in chlorine ions, what is the concentration or the molarity of the ions if we're not counting positive, negatively charged? So the solution is actually 2 molar in sodium and for this solution, that'd be actually 2 molar in sodium and chlorine ions. Now, if we took another solution, say we took a 1 molar solution of sodium sulfate, well, there are actually for every formula unit of sodium sulfate, there are 2 sodium ions and 3 sulfate ions. And so if we have this solution, we say that it is 2 molar with respect to the concentration of sodium ions and 1 molar for sulfate ions. If we were to total up the total concentration of ions in solution, we would call it a 3 molar ionic solution. So 2.0 molar plus 1.0 molar would be 3.0 molar completely. And just like there are strong acids and bases, there are also strong electrolytes and weak electrolytes. So strong acids and strong bases, and weak acids and weak bases. There are strong electrolytes and weak electrolytes. Strong electrolytes, they conduct electricity very well. The reason why is that they fully dissociate into ions in water, just like strong acids fully dissociate into ions in water. Weak electrolytes, however, only partially dissociate. So some of them, if we go back to some of our chemical formulas, some of them, like if this was a weak electrolyte, some of it would break into sodium ions and chlorine ions, but some of it would stay as sodium chloride. Now this is actually a strong electrolyte, so that wouldn't be the case for this example, but that's just a general example for weak electrolytes. So a weak electrolyte only partially dissociates into its ions in water. A lot of it stays as the formula unit. And then some things are called non-electrolytes. They do not conduct electricity in water. And these in general are things that are molecularly bonded in nature. There are also some exceptions to this, which we'll be looking at in the next video on solubility. So continuing on with this concept, if you want to find out if something is if a compound is ionic or molecular, a strong electrolyte or weak electrolyte, you can follow a flow chart like this. Is it ionic or is it molecular? Well, if it's ionic, it's a strong electrolyte. So all ionic compounds are strong electrolytes. If it's molecular, it might be an acid or a base. If it's an acid, you have to ask, is it a strong acid or a weak acid? If it's a strong acid, we say it's a strong electrolyte. If it's a weak acid, we say it's a weak electrolyte. If it's a base, we ask if it's a strong base or a weak base. Strong base, strong electrolyte. Weak base, weak electrolyte. If it is neither an acid nor a base, we call it a non-electrolyte, and it will not conduct electricity at all. So using this flowchart, you should be able to categorize any compound as long as you know whether it's ionic, molecular, acid, base, or neither, and then strong acid, weak acid, strong base, or weak base.